Hello guys, welcome back. This is our second class of our course where we are designing bridge, press-trussed bridge made of steel, concrete, and tendons that all compose the idea of press trussing. Okay, in this class, I'm going to resume the first class where we saw how we are going to design our bridge, and we knew how the bridge was conceived. It's made of a 3-span bridge, 4 girders, and a deck haunch, and a girder. The girder is made of a cross section of a BT 72 high. Our deck is deck of TS, the thickness of 8 inches. Our haunch is made of 1 inch thickness, and well, let's begin our class. So as I said, guys, you are going to take a PDF document where you can follow the instructions down here that I'm going to discuss in the classes. And we saw that we have to use a load truck in our designs, and this is very important in order to get the loads and the resistance that we are going to take out from the bridge. All right, this idea of a dynamic load allowance impact of 33% we are going to discuss later on this class and on the course. All right, this is our load truck, the designing truck that we are going to use, made of 3 axles and with 8 kips and 32 kips. We are going to use both distance here 14. All right, when we put the load on the bridge, the load of the truck on the bridge, this is the main idea of how we are going to use the loads, the load lane and the load truck, right? If we had chosen to use the tandem approach, this would be the loads that we had to use, but it's not the case here. This is the design we are going to see specifically in the 5th class. All right, we are going to discuss when we have a multi-span bridge, a continuous bridge. All right, even though we are using a methodology or a technology that made of girders that don't allow for us to have a bending moment on the piers. This is the idea of where we are going to use. What we have to do here is just to put a roller here, all right, so we won't have negative moment on the piers, on the support. All right, this is our declarations of our variables, the TS of our deck. When we use designing the deck, we are going to use 7.5 inches, but when we are taking the self weight of the deck, we are going to use 8 inches. All right, our FC prime 4 KSI for the compressive strength of our concrete for the deck. Our concrete unit weight is 0.15 kcf. This are the declarations for our precast concrete beams. It's made of a FC prime I because it's initial, all right, at the transfer. So that's why I call it I, actually. All right, we are going to use different unit specified concrete strength for the deck and another for the girder. All right, this is because we are thinking about make economy when we are building the whole structure. All right, and when I think about our concrete at service loads, we are going to use our F prime CS of 7 KSI. All right, the length of our bridge are 120 here in our sketch of the bridge. All right, 3 spans, span number 1, span number 2, span number 3. I put it here. Just a deck with a wooden surface and a barrier, just in order to show you guys how the bridge is going to be at the end of the day, all right, when we finish building it. So these are the tendons or the pre-stressing bars, all right. Have a haunch tendons and the linear tendons down here, the bearings. Thinking about a simply supported bridge, this is why we won't have negative moments here, because I have a separation between elements, right? So we won't have negative moments over the piers. So this is our bridge. So let's continue here. You can follow by the use of a PDF paper, or you can take these exercise into the MathCAD software. So you are going to have the possibility of changing the variables, the numbers. So you are going to study any other bridge, span, a number of girders, whatever. All right, you are free. Use this material as you will. This is a sketch of our spans, the area of a strand we declared in the first class. Our FPU, it's the specified tensile strength for our strands, right? Tension that we can use for both yield strength of the strands. Can see in the table down here numbers that we are going to use, the modulus of elasticity of our reinforcing bars. We are going to use a future wetting surface made of 2 inches thickness, all right. Our barriers, or you call it New Jersey barrier, all right, made of unit weight of, or a self weight of 0.3 kips foot per side. The area of the BT72, it's up here. You can take it from a table also in the ASHTO tables, or consult the fabricators, all right, tables. These guys that work with this kind of structure and designing, they also have their own tables for area, for moment over nature, for section modulus. So this is our declaration, all right, because we are going to use it later on the course. This is a picture of our girder, the area, how it's made, right? So I use this information here, and I put it on the AutoCAD. So here in the AutoCAD, I could study the properties of the girder, the cross section, the area, the perimeter, so on. So it's easy for us to define the centroid of a region, since you know how to use AutoCAD in order to take those informations. All right, so I got some of information about the girder, right? This is a table that we are going to use for understanding how the material used on the design weights, all right? I explained for you all the terms that we are using, how to find the modulus of elasticity for the concrete of the girder, the concrete of our deck, concrete of our barriers. And this is our lesson number 2, where we are going to study the section details of our girder, all right? We are going to use a space between girders of 12 feet, all right? So how can I find the effective flange? So what is a flange? The flange is the part of the deck, the slab here, that you use in order to understand how the loads, or how much of the loads of the truck is going to this girder and not for the other girder. This is an interior girder. So how much of the load it's going to carry and this is the load that you are going to use for finding bending moments and shear stresses and whatever. We have to find the modular ratio between the slab and the beam concrete since they are different. So we call it N, N. So the modular ratio is taken when you divide the modulus of elasticity of the slab by the modulus of elasticity of our girder. So we got this number here, 0.7559. We are going to use it in order to see the performance, the behavior of our composite section. All right. The transformed section properties are: the effective flange width must be transformed by the modular ratio to provide cross-sectional properties equivalent to the beam concrete. So I am multiplying the flange that we found here, all right, by the N, that our modular ratio. So in the end of the day, I'm not taking real area, but a area when you take different materials into just one section. All right, this is the main idea here. So our transformed flange area is going to be thickness of our deck multiplied by the flange width multiplied by N. So this is our area in the end of the day. All right, it's different when it's a different number when you take only the area of the deck. Let me show you what I'm talking about here. If I take the area of this flange here, so let's use the number command area in AutoCAD. So I've got the area, the real area of 1080 inches square, but when we multiply it here, I've got another area because number N is lower than 1, so I am going down with the area. All right, so that's what happened here. If you guys get any doubt, please leave a comment down below, so I'm going to have a much pleasure helping you guys solving these or any doubt that you got in this course, right, throughout this course. So the transform flange area moment of inertia is IFGT. It's just when you take the area of our deck flange times the thickness to the third divided by 12. I've got 3,826 inches to the square. I leave highlighted here only the structural thickness of the deck, 7.5 inches is considered. All right. So in the end of the day, we are going to live with this cross section here. This is our cross section, that our composite section that we are going to use when we put the strands down and up here, and we're going to analyze it again. All right, later on the course. So these are the dimensions that I've got at the end of the day. So the HCW 42, it's half the haunch width. All right, haunch is this guy here in red. So we use it when we are planning to build a bridge that has a displacement for making the waters from rain to flow correctly. All right, so sometimes you have to use this additional element on your bridge. All right, so this is our moment of inertia of our haunch. The haunch width multiplied by the haunch thickness divide to the third divided by 12. So we've got here 0.331 inches to the square, right? This is a picture where you can find the information from our composite section, right? This is a table where we can sum it up. All right. So the beam area, the haunch area, the deck area. So in the end of the day, we got a composite section with area, the sum of the three elements. All right. This is the centroid of the three elements. The multiplication area. So I've got multiplying the area by the centroid, so you got this number. First order moment. So when you study this section, in order to take the information using the find the parallel axis theorem, all right, the second order moment, and in the end of the day we are going to have the moment of inertia of our composite section. All right, so this is the declaration. AC is our area of the composite section. It has a height of 80 inches and a moment of inertia of 1,175,000 and 0.776 inches to square. So if I divide the sum of our area multiplication here by the area of our section, I'm going to find the distance from the centroid of the composite section to the extreme bottom fiber of the precast beam. All right, so you can find it also using the AutoCAD, so it's not a problem here. I'm just proving you that you can find by this equation here, or you can find simply in the AutoCAD software. So the distance from the centroid of the composite section to the extreme top fiber is when I got the height of our girder minus the centroid of the composite section. This is the distance between those centroids. All right, so I've got here finding the centroids and the modulus of our section when we take the composite section, not only the girder. So from now on we are using the composite section in order to find the modulus of the section from bottom, from the top. So you can see it here. So this is a final sketch of our composite section, the centroid of the haunch, the centroid of the deck, the centroid of the girder was down here below a little. So in the end of the day, the centroid of the composite section that is most important here is 57.2 inches from top, from the bottom of the girder. All right, see you guys in next class. I hope you guys enjoyed this class. I hope you had got any doubt. Please write your comments down below. So this is going to be my pleasure helping you guys. So this is the end of our class. See you next time.